set of talks, we have David Sanders and Luis Benet from the University of Mexico talking about bounding functions and solving ODEs rigorously, Taylor models.
Hi, everybody. So this is work we've been doing recently as an ongoing part of a multi-year project. So what's the motivation? We want to be able to find and prove the existence of periodic orbits in dynamical systems, for example. And so one possible dynamical system would be the solar system. And there's this asteroid called Apophis, which may hit the Earth in 2029. And so given its initial conditions, we want to find out if those initial conditions, when we evolve them under some ordinary differential equations, will or will not hit the Earth. So what is the goal? The goal is to actually solve ODEs, ordinary differential equations, in a rigorous, mathematically rigorous way. That means that the result is actually guaranteed to be correct. So what we're going to try and find is what's called an enclosure of the solution of an ODE given an initial condition. And so that will be some kind of tube that is wrapped around the actual true solution of the ODE that we can't really calculate. So how are we going to do this? We're going to use something called a Taylor method. It's a method for solving differential equations, and that will enable us to construct an accurate solution. How accurate is that solution? Well, we don't know. So what we actually want is a bound that tells us that we have the accurate solution plus the bound, and that the real solution is somewhere in that set. And so that bound will take the form of an interval. And so to do all of this in Julia, we're going to use a combination of packages that we've been developing, basically Taylor series, which, as it says, construct Taylor series of a function. We use that in Taylor integration to do the integration of the ODEs. Then we have interval arithmetic, which does the bounding in terms of intervals. And this all comes together in a new package, Taylor models, which hasn't been released yet, but it's on GitHub here, that we're going to be talking about today. So what is this Taylor method to integrate ODEs? So if you're not accustomed to this, it's pretty amazing. It basically gives us a way to construct arbitrarily good solutions, arbitrarily accurate of ODEs. So here's an example of solving the Lotka-Volterra equations. And so what we're actually doing here is taking this initial box, so this initial condition 1, 3, initial box of initial conditions, or a cloud of initial conditions around that point, and we're evolving that whole box using these Taylor methods, and you can see how that initial set stretches out. So we're not sampling points in this box. We're actually calculating how the entire box evolves under the dynamics. So I'll show you later how we can do that in Julia in a few lines of code. So what is a Taylor model then? So that was a non-rigorous picture. So this is not yet, we don't quite yet have all the error bounds correct, right? So this is, but now what is a Taylor model? So here's an example of a Taylor model for the exponential function. Okay, so that's taking a while. Let's carry on. Sorry. So it's supposed to draw. Yeah. Okay. So one way of bounding a function is using these intervals. So here's an interval. We put it in a standard Julia function, and what we get is some kind of bound of the function itself. So here's the function plotted over that interval, and when I apply this interval arithmetic to this original interval, we get this vertical interval on the y-axis as the result, which we see as an overestimate of the function range, but it definitely includes the true value of the range. And so we can actually improve that approximation by mincing, and that's not going to work either. Sorry, I don't know what's going on. Okay, so what is interval arithmetic? Quickly, in one slide, it's just define mathematical operations on intervals so that the result of an operation is a new interval, and that new interval contains, in a guaranteed way, all the results that you would get by applying your function to the original interval. So here's an example of squaring an interval. We can actually define for any values of the lower and upper bounds of the interval, what the result of squaring that interval will be in such a way that the result always contains the squares of all the numbers in the interval. And so if we do that for all the mathematical operations, then when we compose a sequence of those functions, the result will still be true for the composed sequence of functions. So if we have some computational graph and we put an interval in, at the end of the computation we'll have a new interval out that will contain the true range of the function that we're operating on. So here's an interesting example where when you draw the function, it looks pretty smooth and continuous. It has a little blip that you can't see, and none of these are working. Sorry. But it turns out that actually this function goes to minus infinity. And you will never see this if you just sample the function and draw it on the computer, because it's such a tiny window where it goes to minus infinity. But intervals are able to pick this up. So how can I get a more accurate approximation of a function? So I'm going to approximate any smooth function by a polynomial. Why a polynomial? Because they're the only functions that we really know how to work with on a computer. In other words, evaluate them and differentiate them, integrate them. And the Weierstrass approximation theorem says that any good function can be approximated by polynomials. And then what we're going to do is express the function, as I said, as a polynomial plus some interval error, which means that f of x lives inside this set of the polynomial value plus or minus some radius around it. And the polynomial that we're going to take is, in this talk, going to be a Taylor model. So a Taylor series, or a Taylor polynomial of degree n. So here's an example of how to do that with a Taylor models package. We're going to define an interval minus 0.5 to 0.5, and we're going to create this variable t, which is some kind of polynomial with an error bound. So here the p is the polynomial, which is just t. These are intervals, interval coefficients. So this is the interval 1 times t, so it's just t. And then, for example, if we do 1 plus t cubed, because I took a Taylor model of degree 2, well, I'm going to not keep track. In the polynomial expansion, I won't keep track of things of order 3. And so those things of order 3 come and live in this remainder bound. So it automatically calculates the remainder bound such that the sum of the polynomial, given any position t within this particular interval that I chose, the actual value of the function 1 plus t cubed will lie inside this tube around it with that width. And so we can manipulate polynomials. So basically Taylor series.jl is a polynomial manipulator in one and several variables. So we can manipulate polynomials, which is what we need to then do arithmetic on Taylor models themselves. So for example, to sum two of these Taylor models, we sum the polynomials and we sum the remainder intervals. Multiplying is a bit harder. We need this B operation that bounds a polynomial, that finds bounds on a polynomial in a box, and that turns out to be actually quite tricky to do, especially in higher dimensions. But the easiest way to do that is just actually to evaluate the polynomial using interval arithmetic. And for elementary functions, we're going to expand the function itself in a Taylor series, and then we know that we have this Lagrange form of the remainder that says that the whole infinite tail of the Taylor series can be written as the n plus 1th derivative evaluated at some point in the interval. And so the way that we're going to deal with that, how do we bound that thing with this arbitrary point in the interval? Well, actually, we're going to use interval arithmetic to do that, because all we need to do is calculate the nth derivative evaluated over the whole interval, and that's what interval arithmetic enables us to do. And so one way of doing that, and there are other ways that might be more efficient, is to use another Taylor expansion, where we expand actually the function, sort of developing it around the interval x, and basically we just expand this f of the interval x plus this little x, which is the Taylor expansion variable, and then the bound will be given by the n plus 1th coefficient in that expansion. And so we can do that in Julia. For example, here's a Taylor series from the Taylor series package. So again, t is the Taylor variable, and sine of t is this expansion up to order 3. And then when we do sine of x plus t, we get enclosures. So these coefficients are intervals which are giving enclosures of the higher derivatives of sine over that interval. And so this is so Taylor series actually provide the way to calculate high derivatives, do automatic differentiation and calculate higher derivatives. And so very quickly, what is this Taylor method? So you may remember that just to prove that solutions to ODEs exist, we use this Picard iteration, and you probably did it even by hand. But of course, now we can just do it with Julia instead. And so how is that? So in Taylor series, we can create we can have Taylor series in several variables. So here I've got 2 variables. And then this little piece of code is just doing the Picard iteration with this integral symbol. So we have this integrate function in Taylor series, which integrates with respect to the first variable, which is t in this case. And there I've chosen to use rational coefficients. And so we're actually expanding the solution to this differential equation, which is, of course, the exponential function. So this is calculating the Taylor series of the exponential function from the differential equation. And then we can do exactly the same thing. And so there are more efficient ways to do this. This is a nice, simple pedagogical way, but these packages have more efficient ways to do this. And instead of, more interesting thing that we're going to use now that Luis is going to explain is what happens if we have an initial set of initial conditions. And the way we're going to do that is by having this sort of analytical initial condition, 1 plus delta A, with delta A another Taylor variable, and then we get a series that's a function of time and delta A. And so that's actually how we solve these Lotka-Volterra equations, doing exactly the same thing, and we get this Taylor series in these 3 variables that describes the evolution of these initial sets. Okay.
So,
Alt R.
No, it is not. No. So what I will do now, it is explain the way of a very naive way of validating an integration of an ODE. And I will actually describe a very, very, very simple example. It is nice because we know the exact solution, and therefore we can compare. So I have here loaded some packages, and some of the functionality I will be using is overloading some functions and some methods in Taylor integration, which are hidden. So if you actually want to get into the details, send an email and we send you the notebook. So again, the idea is we have this differential equation, x dot equal f of t and x, and we have an initial condition. Now that initial condition will be a number, something like this, plus another variable which will represent tiny deviations within a set of the initial conditions. So it is not a point initial condition, it's actually a set of initial conditions. And that variable is something we will be carrying on. So as David explained, we will have this type of solution, the Taylor model solution, which is a part with a Taylor expansion, all these sum very awful, and then some remainder. The idea is that the exact solution lies somewhere within that Taylor model for all times within a given interval, the integration interval, and for all initial conditions within the set we care. So the example I will be describing is this one, x dot equals x squared. The nice part of this example is that the solution exists. You can do it analytically. You can actually write the exact solution, which is written here. And I will be using the initial conditions, which are delta will be a small variable, which is inside this set. And therefore, the actual set of initial conditions will be this capital X of delta. Now, the nice part of this example is that actually you can see that there is a singular point in t. So at some point in t, there is no solution. And we should not cross that time. And the time is given actually by this. So it depends on the actual initial condition. We should not cross that time. So again, this is to define the function that we want to integrate. This is the exact solution, just to compare at some point. Sorry, or whatever. So what happened
You have
here?
to press the cursor.
No, it is not. Oh, yeah. And I will define some parameters that Taylor integration requires something which is called some absolute tolerance, which allows to determine the time step. It will be essentially a non-constant time step, order 3 in time, so it will be a t to the third Taylor series expansion, and second order on those initial, in this delta parameter, in the tiny changes in the initial condition. This is to define simply the initial conditions in a nice way. This is saying that we will have a Taylor expansion in n variables, in this case 1, on the initial conditions, and the rest it is the time part. And the time we should not cross is actually the infimum of this interval. So whatever we do, we cannot get beyond that number. This is again the same. David already explained how to get the coefficients of the series, and we do precisely that. And the upper part is showing actually a non-validated Taylor expansion in T. This is somewhere written here, whose coefficients are actually a Taylor polynomial on that delta, and those things a priori contain the solution for any initial condition in a tiny interval. Now, this is not yet validated. And just to compare whether things are doing well or not, you can check the Taylor expansions on those things for, so here it is the exact solution, here is the proposed solution, only the last coefficient, just to see that things are sort of close at least. So how do we get the time step? The time step uses this parameter, this absolute tolerance, and essentially the last 2 coefficients of the expansion. There is some norm, some powers. I will not get into the details. If you want to know the details, see your talk last year in Julia Cohen. In any case, we get this number. So it is a tiny time interval what we are going to be integrating. How do we bound the remainder? So, well, this is the formula that David explained before. The point is that we have to do an integration over the whole time interval that I just described, which is done here with Taylor integration. And we get that a priori interval that is the remainder gives me this, which is extremely small. It is truly small. But this is not yet validated. So what we do to validate actually the solution is that we use that delta test, that proposed remainder, and we have to satisfy this enclosure relation, which is not quite clear here. So the reason is that if we do satisfy that, then there is a nice fixed point theorem by Schauder, which tells me that the solution exists and is unique. So we're actually doing in the computer some maths. So I have written a function which is called validate existence, and we get a remainder which actually truly bounds the solution. And what that means is that this contention is actually fulfilled. So here I am checking whether the exact solution in the whole interval is within my solution, the Taylor model solution, and it holds true. And just to describe how good the result is, well, a priori one has to reset the initial conditions and iterate everything, and I couldn't actually resist to put something like go to 1. And now I will do a more serious integration of this problem. So what have I changed? The absolute tolerance is not 10 to the minus 8, but 10 to the minus 20. The order of the time of the polynomial in T is 24. I have order on this variable in the initial condition being 4, and I will simply go ahead. Now, this is the initial conditions again. And this is the result of the integration. And what I want you to see is that at the beginning we have some tiny, this is the actual time evaluated, this is the time step, and this is the diameter of actual box that is being proposed by the solution. So the solution lives somewhere here, 10 to the minus, well, I don't remember the remainder for this case, but it was truly small, and it begins growing. So this very naive approximation, the most naive you can actually do, will have the problem that the remainder, the box actually enclosing your true solution will be growing. So one has to do a little bit more work to actually keep the close to interesting cases. And this is the result of that integration. So the red lines, since this function is, the exact solution is actually growing, we can compute from the edges of the interval where will be the solution, and the true solution, the exact solution, is bounded between these two red lines. The blue error bars are actually the computed solution at different times. But actually recall that I do have a polynomial in between each of those integrations, so from this point to this one. So I may evaluate at the say end point of the time interval with the integration, but I may also evaluate at any point. So actually I have a polynomial on time and on delta, which has the solution in every single piece of that interval. And I mean, I am a physicist, not a mathematician, but as a physicist, I'm really excited about this. So just as a very, very, very brief summary, so Taylor models allow to bound rigorously sufficiently smooth functions. This is what we couldn't see in the demo of David.
Let me try and...
ODEs can be rigorously solved, bounding the exact solution. And actually, we have many things to be done. So if you want to join us, please approach us or send us an email. And we have to thank the financial sources. So thank you very much.
David, you want to try and show your code?
Yeah, I'll try and do it, yeah. I mean, you can have questions in the meantime.
Okay, thank you very much. Does anyone have questions for the speakers?
Thank you very much for this very interesting talk. I may have not understood something, but you presented this rigorous approach, and this is rigorous from this numerical perspective, but are all of these things that you presented also proven, like in the mathematical sense, analytically proven that this is a subset and everything is fine?
So I think one of the assumptions is our code is correct.
Sorry?
So let me first assume that our code is correct.
Okay.
I'll take that.
No, so the answer is yes.
Yes.
Okay.
Exactly. But I mean, in the sense, on the numerical sense, I mean, we need that assumption. But the thing is that we have this fixed point Chalder's theorem, and that stylizes everything. We know that the solution exists and is unique.
So what we're saying is that we have a function on an interval. This is what I'm trying to show in this picture. Here we go. Okay. So what are we showing here? So this is the exponential function over the interval -5 to 5. And this is the approximation given by, not an approximation, this is a bound, a rigorous bound given by a Taylor model. What is the Taylor model? This is the Taylor polynomial. In this case, it's of degree 1, so it's a straight line. And then we have an interval bound. So we have the straight line, and at each point of the straight line, I add the interval to it. Okay. So that gives me this bound, and now I'm going to change the degree of the polynomial. And as I change the degree, okay, so it's still pretty huge, but as the degree gets bigger and bigger, we see that this region, which is given by this Taylor polynomial of degree n plus the interval at each point, is always enclosing the entire function graph. That's the point. And this is rigorous. This is rigorous in a mathematical sense.
So in the limit of infinite order, you converge to the exact solution.
Yeah.
All right, thanks. That's exactly my question. Yeah. Okay.
Right, but you can't go to infinite order. That's the point. And so in order not to go to infinite order, we have this interval bound. But if we go to high enough order, then the interval gets really pretty small. So this is still an enclosure of the function over that entire thing.
Thank you.
And you know how far away you might be from the true solution because you have the size of the interval tells you that.
Do we have any more questions? If not, I'd like to ask one. So is this approximating the numerical solution or the true solution in the interval bound?
So the solution of the ordinary differential equation is a function, and this method, if you do it correctly, gives you one of these Taylor models that strictly includes the true exact solution of the ordinary differential equation in a set that is not of width 0, right? It's of width delta, where delta is the size of the bound, but you can explicitly calculate that size. The true solution is inside that set. You're finding a set that is guaranteed to contain the true solution, but that you can, by taking the order of the Taylor series higher and higher, you can get a better and better bound on that solution.
Yeah, so
That goes to 0 in principle if you don't have these divergences.
you mentioned the application of, I don't know, modeling a comet or something like that, right? Isn't there also error because of the physics?
Yeah, sure.
Okay.
So
That's actually what you can, what you would like to put, say, in the parameters of the model or in the initial conditions. Your model itself is, in a way, an approximation, so you are actually testing the validity of your model if you ever have measurements to contrast.
Okay.
But if
I'm not sure whether I have answered the question or not. I mean, the point is that this plus delta included in the initial conditions, you do have them in the initial conditions, but also in the parameters of your model that are at some point measured.
Okay, here's a more mathematical question. Can you do this in the presence of noise? I guess that's the issue.
So this is for deterministic dynamics.
Yeah. Right.
If you have noise, then it's a different kind of situation, I think. Because the noise could be, in principle, if you have a Gaussian noise, in principle, it could be arbitrarily huge, right? With a tiny probability, so you can never bound that in a rigorous way.
Right. Okay.
I mean, you could say, I guess you could fix an interval and say, within this interval, I have probability, 95% of being, or something, but.
Do we have any more questions? Okay, one last question and then we'll have to finish.
So given that most systems are chaotic, I would imagine that after some time limit, these boxes become so large that are they still helpful for chaotic systems after some?
Yeah,
let's say
you just use big floats with large precision.
All right. Okay. I see.
And so I mean, this is Julia, so you just put a big float into the Taylor model instead of a float, right?
Okay. All right. Thanks.
Yeah. So I mean, obviously, there's a limit to how useful that is because of the chaoticity. But if you're looking for unstable periodic orbits, for example, then you can certainly do that.
Okay, if we
And
could all
that's on the cards to do.
if we could all thank the speakers once more.